Bless you. Happy Friday. When we left off last time, we were trying to evaluate this integral. We have the region plotted. Right, and the solid of integration is what's inside the orange, right, but above the blue. We saw that the curve of intersection between the plane and that paraboloid is a circle, specifically the unit circle. So we have a base, a circular base with a height. So we decided that cylindrical would be the best. And we just described the region in cylindrical coordinates before we ran out of time. It was square root of x squared plus y squared, right? Yeah. Cylindrical, the generally used order is dz, dr, d theta. All right, in this case, we notice we're going to have to do dz before dr, right? Because z is dependent on r. Now we need to write the integrand in cylindrical coordinates. It's already there. Square root of x squared plus y squared in cylindrical is what? It's just r. We now need to convert the volume differential into volume in terms of cylindrical. Well, it's fairly straightforward. In fact, it is the exact same as polar with an extra dz. So in cylindrical, dv is r, dz, dr, d theta. Is there a theta anywhere in our integrand? No. Are any of our bounds dependent on theta? No. The outermost integral is going to wind up being 2 pi. Oh, look at that. There's no z in the integrand either. Ultimately, we're left with 2 pi times a single integral 0 to 1 of r squared minus r to the 4th dr. That integral is going to be the most work we have to do in the evaluation. And it's really not that much work. R cubed over 3 from 0 to 1 is a third. R to the 5th over 5 from 0 to 1 is just a fifth. Five minus 3 is 2 times that 2 pi over 15. There's the integral. Well, that was easy. The setup was difficult. What you're going to notice, setting up as an iterated integral is the most difficult part of multiple integration. The actual evaluation itself is typically very simple.
So we got the 2 R's and then that can be linked to them. So the first R was from converting the integrand from rectangular.
Yes.
The second R is just because.
dv is r dz dr d theta, yes. So the first r is the integrand, the second r is from the differential. In cylindrical. In spherical, dv is something different. Right, remember, it's rho squared sine phi d rho d phi d theta. In spherical coordinates.
Right, I meant the other R. Second one that we got.
Yeah, so whenever you're in cylindrical, that's always what dv is going to be. Now again, you could change the order of the differentials. It could be dr dz d theta, right? But you're always going to have r and then those 3 differentials. This is the accepted order. This is the order that's used most often, so it's the order that I'm probably always going to use. We're going to integrate x squared plus y squared plus z squared over the ball of radius 2. Ball of radius 2 is just a sphere of radius 2. Oops. What happened? There we go. So how would we describe that?
Rho is between 0 and 2.
Keep going.
Theta is 0 to 2 pi. and phi is pi over 2, negative pi over 2 to pi over 2.
You have the right length.
Here, pi.
And so phi you can't change like you can with theta, right? You can say theta would be like negative pi over 2 to pi over 2 if you want the first and fourth quadrants. Because phi is an angle of declination from the z-axis, it's always going to be between 0 and pi. The easiest description. Again, the accepted order, the one that is typically used, d rho, d phi, d theta. In spherical, what does our integrand become? It's not rho. It's rho squared. And now, what is dv?
Sine phi. D phi.
There's no theta. Oh, rho doesn't depend on phi. Remember we said the integral from 0 to pi of sine of x was 2. So I can just get rid of that right now. And write this as 4 pi times the integral from 0 to 2 of rho to the 4th d rho. Rho to the 5th over 5 from 0 to 2 is 32 over 5. 32 times 4, 128. This integral is 128 pi over 5. Find the volume of the solid enclosed by the paraboloids z equals x squared plus y squared, and z equals 8 minus x squared minus y squared. Let's take a look. Z equals x squared plus y squared, and z equals 8. It's x squared minus y squared. Let's go -5 to 5 all the way around. Nope. Okay. Z. Maybe up to 10. Okay, that's good. So the solid that we're trying to find the volume of. Right, it's enclosed by the two paraboloids. It'll be this region in here, right? Do I want? What if I set? Opacity of the orange one. Nope, it has to be the blue one. Of course it does. Right, so it's what's inside the blue, the orange that's inside the blue. Right, that's what we're looking for. That's our solid. I'm not going to rechange the opacity because I want to be able to see through everything.
Why is it not the upper part too?
Because that's not enclosed by the blue. It has to be enclosed by both paraboloids. Oh, wait. It might be enclosed by the blue, but not the orange. Notice the orange is now outside of the blue. So that'll only be enclosed by that blue paraboloid.
The orange in this. It's like
No, you're right. It would be this entire thing. Yeah, you're right. So I'm definitely gonna need the opacity for both. That's kind of a good angle right there. Oops. Finally get a good viewing angle. I hit the wrong button, of course. Copy. And we're not even going to play games. I'm just going to go ahead and save it as a picture. Okay. Now remember, volume is just the integral over the region, right, of the volume differential. That means we have to describe that region. You have three choices: rectangular, cylindrical, spherical. Right? It depends on how you want to describe it. They should all be doable. Because it's not like we have an integrand. So you should be able to do it easily. You should be able to do it in all three coordinate systems. Obviously, one of the three is going to be the easiest. We just have to decide which one that is. So what are we thinking? Well, I mean, we're in the section on cylindrical and spherical, right? So clearly it's going to rule out rectangular. Doesn't want to play devil's advocate and go spherical? No, neither do I. Cylindrical is your best bet here. I mean, if we take a, I want you. If we take a look, again, let's just look straight down on it. You can see the curve of intersection is a circle. Again, you can also easily do this by just equating the two. Setting the two z's equal to each other and solving, and you find out very quickly it's a circle. Winds up being x squared plus y squared equals 4. Which is a circle of radius 2. That would be our two-dimensional domain of integration. Then we just have the height left, the z-axis left. Clearly cylindrical. I'm going to start with the two-dimensional circle first. Describe a circle of radius 2 in polar, which is r theta.
would be from 0 to 2. And theta would be from 0 to 2 pi.
Like, 'cause remember in cylindrical, r theta is the same as polar r theta, right? So we can just do that. Then we just go, okay, now the height extends from what to what? From the orange, right? Up to the blue. But we need to write that in cylindrical. So the orange in cylindrical equation or in cylindrical coordinates is what? Z equals and then goes up to the blue. Blue represented in cylindrical. Z equals there's your solid.
Question, how is 0, or I'm sorry, how is R between 0 and 2?
So r theta is the two-dimensional domain, which was a circle of radius 2. R represents radius. Right, so technically in polar, r is the distance from the origin to the point. But if you're talking about a circle, then it would just extend from 0, right, to whatever the radius of the circle is, because the farthest you can go is actually on the boundary of the circle itself, right, which is the radius.
So wait, how do we know that the radius?
Set the two equations equal to each other. You'll wind up x squared plus y squared equals 8 minus x squared plus y squared. When you solve that for x squared plus y squared, you get 4. Right, you have 2x squared plus 2y squared equals 8. So x squared plus y squared is 4. Right, so it's the same as when you're trying to find point of intersection of two curves, you set the curves equal to each other.
Yeah.
We're finding the curve of intersection because we're dealing with three-dimensional objects. But it's found the same way. You just set the two surfaces equal to each other. And that'll give you the curve of intersection.
And that's how we found D to set them to 7.
So Z is different. So Z you want to look at, because we just described it in polar. Z is going to extend from what to what in the region, right? It goes from the orange up to the blue. Again, because you have to be any point within there, right? So if I'm here, right, some point in here, that is bounded below by that orange curve, bounded above by the blue. And in fact, no matter what point you pick in that region, those are always going to be your upper and lower bounds, right? So any point will extend between those two surfaces. Because we decided to do cylindrical coordinates. But you can also do spherical. Well, r theta is polar, right? So when you're in cylindrical coordinates, the r and theta are the same as polar. So really you can think of cylindrical as polar coordinates with height, which is where the z comes in. Well, polar we wouldn't be able to do because it's a three-dimensional. So polar is two-dimensional region, right? But when you're doing cylindrical, you can kind of break it down into the two-dimensional polar region and then define height. That gives you your cylindrical. Does that make sense?
Yeah.
Right. So by the way, we did a triple integral where I wrote it as a double integral over a domain and then single integral with respect to z, right? That was when we were doing triple integrals. And then I described d as in polar. What I actually did was cylindrical coordinates without actually saying it was cylindrical coordinates. Right, because that is essentially what you do in cylindrical.
Okay.
Right, so volume is just the integral over the region. And then the volume differential. R dz dr d theta. Neither z nor r depend on theta. I'm also going to eliminate the z because there's no z. Right, so the integral with respect to z would just be 8 minus r squared, the upper bound, minus r squared, the lower bound. Volume would then be 2 pi times the integral 0 to 2 of 8r minus 2r cubed dr. That's 2 pi. So it's 4r squared from 0 to 2. 4 times 4, 16. Minus 2/3, I'm sorry, 1/2 r to the 4th from 0 to 2, which is 4. I'm right, yeah. No. Why was I saying divided by 4? It's divided by 2, isn't it? It's a 1/2 r to the 4th. So it's 16 over 2, which is 8. Arithmetic is hard.
Step again where you, I get the part where you just brought the 2 pi outside because G theta didn't, apply there. But could you actually expand out the part where you put, these in the integram? Because I'm not sure how, what you used to do that.
Did the same thing. So there's no z,
Why
right?
is it-
Because it's a function of r. And we have to integrate with respect to r.
So you just have to put.
Yeah. Right. So technically that 2 pi is inside the integral.
Right.
But because it's a constant, you can factor it out of the
Right.
integral.
Okay, so it's just. you
Yeah.
put-
So if that z were constants, I could have factored that out as well and
Right,
written it
so
on
you
the
did
outside.
same thing,
Yes.
just they're just-
But because it is a function of r, right? Because z depends on r and we have to integrate with respect to r, we have to actually keep it in, right? It's no longer constant. You can't just factor it out.
Okay.
So 16 minus a is 8 times 2 pi. Our volume is 16 pi. And again, those are just little tricks that I picked up in my years of doing multiple integration to try and save time. That probably also comes from the fact that I've started to program a lot. And you always want to write it so it takes the least amount of time. So now I just try to always do everything that takes the least amount of time. Which, by the way, is not math. Math does not tend to be efficient. You want efficiency, that's physics. This one's good. Find the volume of the ellipsoid. X squared plus y squared plus 6z squared equals 100. There's probably a geometric formula for it. I don't know it off the top of my head. And I don't care because I can do triple integrals, which is a much more efficient method in my opinion. That's just because I hated geometry. The only math class I actually put effort into and got a C. Good. See how this turns out. This should work. You know what? I'm going to take the lazy man's way out. Except I don't need the contour style anymore. Yes, that worked. So there is our ellipsoid. This color kind of looks like an Advil. Let's angle it just a little bit to get an idea. So we need to describe this region. Again, the start of the battle is you have to pick a coordinate system. You want to try and define this rectangularly? No, I definitely don't. So that leaves you now between cylindrical and spherical. So how do you want to do it? Why do you want cylindrical?
To solve for Z.
Let's play devil's advocate for a minute. And you go, well, a sphere is just a special type of ellipsoid, so spherical. Theta is easy to describe, 0 to 2 pi. Phi is easy to describe, 0 to pi. Bro. Rho will go from 0 to something very, very hideous in terms of theta and phi. Right? Because the radius of an ellipsoid is not constant. So it'd go from 0, the origin, out to the edge of the ellipsoid. So you'd have to write the ellipsoid as a function f of theta phi. And that would be the upper bound for rho. Versus if we do cylindrical, theta is still 0 to 2 pi. R is what? Zero to 10, right? Because you're only looking on the XY plane. On the XY plane, this is a circle of radius 10. To define the height, Z would just go from the bottom portion of the ellipsoid to the top portion of the ellipsoid. This means you want to write Z as a function of R theta, which is extremely easy to do. In fact, it wouldn't even be a function of theta. It's just a function of R. I'm going to represent the ellipsoid with a script E. Z. Right in cylindrical. Be 100 minus R squared all over 6, right? What letter do I want to use? Is there a Greek letter that looks like Z? Because if there is, I'm going to use that. No, I don't have math type on my hotbar. That's not good. Oh no, I don't have it on my desktop either. Oh dear. I have to search for it. Yeah, that's nice. Don't care. There you are. Oh, that's a bummer. There are none that look like Z. Capital. Yes. Perfect. Okay, the problem is. Looks just like a capital Z. That's fine. That is capital Zeta. Let capital Zeta be 1/√6 times the square root of 1 minus R squared. That's the positive square root of what we had above. Then isn't Z going to go from negative zeta to positive zeta? Again, this is a very common practice in mathematics and physics. If you have something that's very long that you have to write out several times, just replace it. Right, that's why a lot of constants in physics are represented by symbols, like the universal gravitational constant G. Or the Planck length. I think the Planck length is h. Speed of light, little c. Volume of our ellipsoid. Right, triple integral over E. We're gonna have a 2 pi, right? With respect to Z, isn't that going to be 2 times zeta? Which I can factor out the 2. Right, 4 pi on the outside. Left with the integral from 0 to 10 of zeta dr. At this point, I'm now going to rewrite or replace zeta with what it should be. Oh, I forgot the R. Oops. R zeta. So R/√6. Looking at that, I'm going, yeah, that integral is definitely not as easy as I remember it being, and it's because I forgot the R.
Where did you get?
The 2 pi for theta, right?
Yeah.
And then if you integrate with respect to Z, isn't that 2 times zeta? I just factored out the 2. And now factor out that 1/√6. This is now simple trig sub. Or not trig sub, I'm sorry. Simple change of variable. U sub. Could do trig sub. Don't know why you'd want to. So we're gonna need a negative 1/2. This one I am gonna write out. All right, then you have square root of u. Antiderivative of that is 2/3 u to the 3/2. So we get 2/3 times 100 minus r squared, all raised to the 3/2 power. Evaluate that from 0 to 10. At 10, that whole thing is 0. So we're going to minus negative. Four pi over 3 root 6 times 100 to the 3/2. Which is 1,000. Volume is 4,000 pi over 3 root 6. Bless you. Right? Or if you don't like square roots in the denominator, you can go ahead and rationalize that. The 4,000 root 6 pi all over 18. 4,000 over 18 will simplify. I don't know what it will simplify to. 2,000 over 9. I think that's as far as it's going to simplify. So it'll be 2,000 pi times root 6 all over 9. Both answers are fine. Fully equivalent. Questions on spherical and cylindrical integration? So multiple integration. Broadly speaking, 3 steps. I guess 4 steps. First, you have to decide what coordinate system you want to work in. Second, you then need to describe your domain of integration in that coordinate system. Third is to set up your iterated integral. And then fourth would be just evaluate it. It is the second step that is the hardest. Describing your domain. Mathematica will make your life a lot easier for step 2. It is not required, but it will save you a migraine. The actual evaluation is usually very simple. Right? And in fact, once you set up your iterated integral, you can just go ahead and plug it into a calculator to evaluate it. Right? I'm not really testing if you can evaluate an integral. That's Calc 1 and Calc 2. I'm testing, can you actually set it up and interpret the integral? The setup will be 70% of the points. So that'd be 1 through 3, right? Describing your domain and then setting up your iterated integral. That'll be 7 out of 10. The evaluation is the remaining 3. So if all you do is just set up the problems correctly, you get 70% on the test. Keep in mind that if you are going to use technology to evaluate the integral, I can't give you partial credit on the evaluation. If it's wrong, right? Because you just plugged it into a calculator. You didn't show me work. At least if you show me work, I can try and figure out where you went wrong. And then award partial credit based on that. So it's up to you. That finishes up multiple integration. I had fun writing this test. Let's say that. Whether that bodes well or not for you is, I guess, to be discovered. I was already in April. Nice. So your Unit 3 test is now available. The only one I'm forbidding you from using is CAS, is the first one. So that one you actually have to do by hand. The other 4, you're allowed to use a CAS. I would recommend that you attach screenshots of the regions that you're using to set up your integrals. I'd also recommend you include the code. Right? This way, if you set it up wrong and you include the screenshot of the region and you have the wrong region, you get partial credit based on the fact that you had the integral set up correctly based on the wrong region. And then I can actually look at the code and see why your region is wrong.
So if we give you the region, we have to do it.
You don't have to use Mathematica.
Okay.
Calplot 3D, Desmos, but you get Mathematica for free as a own student, so why not use it? Right, why not take advantage of that? You're paying for it anyway in your fees. Again, screenshots can be uploaded as separate files. That's fine. Just make sure that either in the file you clearly label what problem it's a screenshot for, or you just, save it as question 2. It's just so I know, what problem it is for. They can be uploaded as JPEGs, that's fine. Test itself, you know the deal. Write out all the solutions on loose leaf paper, save it as a single PDF file to upload. With the exception of the photos, I will not accept more than 1 file upload. Right, you can use notes, textbook. No, they can be separate JPEGs. Just again, make sure that they're clearly labeled. May use your notes, textbook, other official course material. Oh. You're allowed to use an integration table. I guess I copied that from my Calc 2. And integration table, you're allowed to use that. And you can't discuss this with anyone. Except for me. Right, you can't Google the answers. Chances are the solutions you're going to find on Google are going to be wrong anyway. It's going to be due before the start of next Friday's meeting. That is the 7th of April. Yes, we do meet on Good Friday. Rowan is not closed. And again, write that statement, you know, you're not going to cheat, blah, 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 blah. And remember, as always, have fun. The report on an application of multiple integration will also be due next Sunday, not this coming Sunday, next Sunday. I'll get that uploaded shortly as well. Yeah, go to Mercy and maybe with questions. Won't need to actually plot this region.
You know, share with somebody.
That's not good. No, you're the odd man out. This is what you get for this 7 days.
I could write it down.
I'm gonna put it on the screen. How the hell did I get that wrong? This was number 18, right?